What's up? My name is Matthew, and in this video we're going to talk about antiderivatives. And that almost sounds kind of backwards because at this point in time maybe you're already antiderivatives. But antiderivatives are basically the reverse process of taking a derivative, and therefore we call them antiderivatives. Let's go through and look at some of the rules that apply to finding antiderivatives, and then we'll go look at some example problems. The first thing we need to know about antiderivatives maybe is what I've already mentioned, that they are the reverse of the process of taking a derivative. And there's a little bit of notation at the bottom of the screen here, and you are of course always welcome to read all of the text that are in these prepared notes. But what we're seeing here at the bottom is some notation that's maybe a little bit confusing. That if f prime of x, if capital F prime of x is equal to lowercase f of x, then capital F without the prime on it is the antiderivative of lowercase f of x. So how did we change the f prime of x, the f prime of capital X? I have to figure out how to say this correctly. How did we change capital F prime into just capital F? How did we get rid of the prime? We found or took the antiderivative. So far, this is sounding very exciting. As we start to acclimate to this process, I want to show you something that's maybe a little bit disturbing. This function, capital F of x, and this function, capital G of x, if you find the derivative of both of those functions, you'll find that the derivative is 2x for both functions. Now those functions are different. So you take the derivative of those and you get 2x. Now what if I want to go backwards? What if I take the antiderivative of 2x? Which one of those functions am I going to get back to? X squared plus 2 or x squared minus 4? And the answer is, and this is where it's a little confusing, you get both of them. You get both of them plus a whole bunch of other ones. Generally speaking, what you get is this. And I apologize that these pre-printed slides say capital F of x inside of what I just circled, because it should maybe have a different name. The point is that it equals x squared plus c. And that capital C is something that you're going to get to know very well. And that c value is a constant. Whether it's a positive 2 or a negative 4 or plus 1,000,000, we don't know. At least not as of yet. So the bullet that comes after that, where it says this means there is a family or class of functions having 2x as the derivative, what it means is that we would need additional information in order to figure out whether it's supposed to be x squared plus 2 or x squared minus 4 or plus 1,000,000 or whatever. Indeed, the derivative of this function, x squared plus c, is 2x, regardless of what the constant value is. So again, in order to take the antiderivative of 2x and arrive at a specific function where we know what the c value is, we would need some additional information. At some point in the relatively near future, we will get to problems where we do that and we figure out what the c value is. But for the moment, just realize that when you take an antiderivative, you are going to need to include a plus c until we get into more specific problems that involve calculating c. You can read that if you want to. I don't know that it's helpful. It might be a little bit more confusing than it is helpful, but you're welcome to check it out. That is the same as what you're seeing. Oh, actually, I like this. What you're seeing in this bullet right there says that this symbol, which kind of looks like a goofy looking S, is a goofy looking S. It's the integration or integral symbol or sign, and it indicates that we're going to be taking an antiderivative. And this symbol operates on this stuff. That stuff is called the integrand, which I won't say very often, but some people use that term, integrand, just like, I don't know, like if you're doing a long division problem, and you're dividing, I don't know, 372 by 5, this is the divisor, and this is the dividend, and this is the quotient, okay? If you're taking a square root, this is called the radicand. All right, so we like to give names to different components of these things. Anyway, what you're integrating is called the integrand. And another component of that, which we talk about below this sand-colored box, is that there's this dx in here. And that dx is telling us that we're integrating, or we're finding the integral of f of x with respect to x. That will become more important as we go along and as these problems become a little bit more complex. But this is definitely a piece of information that needs to go into your notes, okay? At some point in time, that's going to become background knowledge. You're never even going to think about it again. But anyway, that's the format, and maybe the most important part of that format is the plus c, taking into account the fact that we don't know what that c value is yet, but eventually we will figure it out. That goofy looking stretched out S symbol is indeed a stretched out or elongated S. It's from the word summa, which is Latin for the word sum, and this symbol was created by Leibniz, a mathematician and philosopher. And as it says, the relationship between sums and integrals will be clarified in a later section. Indeed, we will be summing a bunch of stuff. In fact, we will be adding infinitely many things that are remarkably close to 0. And when we add them all up, they'll equal something definitive. We'll get there. Some antiderivative rules. I did say that there were going to be rules for integration, and here is a big one. All right, this one you need to be aware of. And what we're seeing here is that if we're finding the antiderivative of x to a particular power n, the result is x, and then you'll notice that we've increased the power, and I apologize, these notes are not zooming in very well, it's looking kind of pixelated, but we've noticed that we've increased the power by 1, we've increased the exponent by 1, so it says x to the n plus 1, and then we're dividing by that new exponent. So we're going to see some example problems of that later, but let's do an example problem immediately. If we had the integral of x to the third, and we were integrating with respect to x, the result would be, now we take the variable, which was x in this case, and we increase the exponent by 1, so now it's a 4, and then we have to divide by that new exponent. And don't forget to put plus c. So this would be your answer. This is called an indefinite integral, thus the plus c. And you could write your final answer like this, or you could write it as 1/4 x to the 4th plus c. This is the kind of thing that I recommend to a lot of students that they put onto an index card. Building this library of review cards is a great idea. And on one side of the card, you would see this. How do you integrate x to the power of n with respect to x? And the answer on the other side of the card would be this, or perhaps you would write out this entire statement, this entire equation, but at the very least the right-hand side of it. And then on that back side of the index card, I would also include some kind of an example of that process that's being described very generally by this rule. There is also a constant multiple. and a sum and difference rule. Just as we have for derivatives, there was a constant multiple rule that said you could factor a constant like a coefficient out of the derivative process. We've got the same thing for the process of reverse or anti-differentiation, otherwise known as integration. So here you're seeing that we're taking the integral of k times some function, and then here you're seeing that the k has been factored out of the integration process. So you could do this, find the integral of f of x with respect to x, and then multiply that k value in after the fact. If you've watched one of my first videos about derivatives, or perhaps you've seen your instructor or professor say this phrase, the derivative of a sum is equal to the sum of the derivatives. In other words, you can distribute the derivative process over addition or subtraction. Here you're seeing that you can do it with integration. The integral of a sum or difference is equal to the integral or the sum of the integrals, or the difference of the integrals. So again, it looks like we're distributing integration over addition and subtraction. So that's a thing that you're allowed to do. It's a rule. Now, let's go back here for a second. This k value that's being factored out of the integration process, that k value has to be a number. It can't be a variable. It could be like a lowercase a that's representing a constant value. It could be an unknown constant, but it can't be the actual variable that you're integrating with respect to. That could not be an x, and that's what we're seeing in this bullet right here. The constant multiple rule requires k to be a number, even if it's an unknown number. Okay, you can't factor out a variable like that. In other words, notice the does not equal sign right there. Okay, can't factor that x out. However, in example number 1, we see an example where we can use that factoring process. We could say that this integral is equal to 4 times the integral of x to the 2/3 power, integrating with respect to x. So let's keep the 4 there and multiply by, and now let's figure out the integral of x to the 2/3. We're going to keep the variable x. I'm going to increase the exponent by 1, adding 3/3 to the exponent makes it x to the 5/3. We then have to divide by the new exponent, so dividing by 5/3, and don't forget to put your plus c. Now the 4 should multiply into the entire resulting integral. Now I'm going to do a couple of things. I'm going to multiply the 4 into this first term where it says x to the 5/3 over 5/3. I'm also going to do a little quick keep change flip. So actually, let's keep the 4. Let's multiply that by 3/5 x to the 5/3. So instead of dividing by 5/3, I'm multiplying by 3/5. Division is the same thing as multiplying by the reciprocal. And then we've got the 4 times the c value. Now c is a constant. And what happens when you take 4 and you multiply it by a constant? You get a constant. So I'm still going to write plus c. Now that's difficult to take notes on. You might want to put in a little note with an arrow here that says this c value actually is 4 times c, but 4 times c equals another constant. Or you could just write 4 times c equals c. It's not ideal, right? That's a tough thing to take notes on. So probably shouldn't use an equation like that. I would write it out using words, that 4 times a constant value is another constant, so we just leave it as a generic c. Clean this up one more time and write this as 12/5 x to the 5/3 plus c, and you got yourself a final answer. That is the family of solutions. It is an indefinite integral, and you have done antidifferentiation. This problem gives us the opportunity to do what we did in the previous example, except we also get to distribute this integral. So I'm going to write this as 3 times the integral of x to the 8, integrating with respect to x, minus 7 times the integral of x to the 3rd, integrating with respect to x, plus the integral of 4, integrating with respect to x. So I distributed the integration process and I factored those constant multiples out of the integrals. Okay, I definitely did two things in one step there, which I don't normally do. In fact, I don't know if I can live with myself. There, all we've done is distribute the integration process. And then you could rewrite this and factor those constant multiples out. And we end up here again. So in going from here to here, I call it distributed. We distributed the integration to the 3 terms, and then from here to here, we factored out the constant from each of those 2 of those new integrals. Now, if you want to be specific, come back here and use the more specific language. We applied the sum or difference rule is what we did first, and then we applied the constant multiple rule. Sum or difference rule, and then the constant multiple rule. I may never write CMR again. You should write it out, constant multiple rule. Okay, now let's do some integration. Equals 3 times integrating. Keep the variable the same. Increase the exponent by 1. Divide by the new exponent. Plus c. Minus 7 times. Keep the variable. Increase the exponent by 1. Divide by the new exponent. Plus c. Plus. Now what in the world are we supposed to do here? How am I supposed to integrate 4? There's no variable. You could put yourself a little note here that says equals the integral of 4x to the 0 dx. A constant term is a term where your variable is to the 0th power. And we don't ever write it that way, but it is there. X to the 0 is equal to 1. So that says 4 times 1, which is still 4. So it's equivalent. And it allows you that opportunity to put the 4, write the variable, and increase the exponent by 1. It becomes x to the 1st power. We don't write that ever either, so I'm going to erase that 1 and put the plus c. The integral of a constant, with respect to x is equal to ax plus c. That shouldn't have a box around it. Maybe it should have some kind of wavy lines around it or something. I don't believe that that statement is printed specifically in these notes, so you might want to put that someplace special. That is the integral of a constant with respect to x equals that constant times x to the first power now, and don't forget the plus c. That's what happened right here from here. So this could go on one side of an index card, and then this could go on the other side of the index card as an example of that process, okay? I'm making a mess. So we've got some cleanup to do now that I've made this mess. Can I get rid of any of this? I don't know if I can erase that specifically. Let's try. It's distracting me. All right, that's good enough. Let's take this thing from left to right again. The 3 divided by 9 is going to reduce. 3 over 9 is 1/3, so I'm going to write that as 1/3 x to the 9. You could write it as x to the 9th over 3 if you want to. I'm not going to write the plus c, because what's a constant plus a constant plus a constant? It's another constant, so we're just going to tack on a plus c at the end of this final answer, okay? So don't write those plus c's over and over again. Let's move on to the minus 7/4 x to the 4th power plus 4x. Finally, plus c. And that there is your antiderivative, your family of solutions. Is there a great way to check and see if I did this correctly? The answer is yes. If you take the derivative of the stuff that's in this box right here, you should get this original expression at the top of your screen. Pretty nice to have a built-in process for being able to check your solutions. You can check to see if you factored correctly by multiplying it back out. You can check to see that if you found the antiderivative correctly by taking the derivative and seeing if you get your original expression again. Rules, rules, rules. Indefinite integrals of exponential functions. So here we're finding antiderivatives of exponential functions. The first one is e to the x equals e to the x plus c. That's nice, and it's no surprise that looks that simple because the derivative of e to the x was e to the x. Now the derivative of e to the kx, the derivative was equal to k times e to the kx. And this k came from the chain rule. We've multiplied by the derivative of the exponent. So, just as a little reminder of that relationship. Now, let's take this equation that I've just written out in blue and divide both sides by k. If we do, then the derivative with respect to x of e to the kx will all have to be divided by k because we divided both sides by that k equals e to the kx. All right, so I isolated e to the kx on the right-hand side. Why? Well, now I'm going to take the antiderivative and I'm going to factor out this division by k. So I've got 1 over k times the antiderivative of the derivative of e to the kx. But since I took the antiderivative of the left-hand side, I must take the antiderivative of the right-hand side. Now, you don't have to know this at all, okay? If you've already started writing this down, great, write it down, but put it off to the side. The reason I'm showing you this, and this we have not talked about yet, and I'm not trying to talk about this in detail right now. However, the antiderivative of the derivative, it's sort of like squaring and square rooting, kind of, okay? They kind of cancel each other out. They're kind of inverse processes. But just for the moment, think of them as kind of annihilating each other. So if these go, what we're left with is 1 over k times e to the kx equals the antiderivative of e to the kx. Now, all of the stuff that I've just written out in blue is kind of a hack. However, on the right-hand side, you see the antiderivative of e to the kx, the integral of e to the kx. On the left-hand side, you see e to the kx divided by k. I'm in the way. There you go. So the plus c isn't in there, and I didn't include the dx's, but I just want you to know that all of these kinds of rules and like the things that you're seeing, you know, that are written under me right here, those aren't just coming out of thin air. They're directly related to stuff that you already know and have been working with. So don't, while you are going to commit some of this stuff to memory as though it's brand new information, I want your mind to know that this is extremely closely related to things that you already know from your study of derivatives within your study of calculus. All right? Allow your mind to make those connections very loosely in the background. I think that ultimately it will help contribute to your success. So these 4 statements that are on in this sort of tan-colored box should go into your notes if you're not already using a printable version of these notes. And let's see if we can use any of those in order to find a solution to this problem. The integral of 8e to the 4y, we're integrating with respect to y this time. I am going to factor out that constant multiple of 8. We'll multiply by the integral. That was a terrible integration sign. E to the 4y dy. Now the integral of e to the, it was presented as kx. Here it's ky. It's a constant value times our variable. So let's keep the 8 out front. Now the integral of e to the 4y is going to be e to the 4y divided by that constant value in the exponent position, which is the 4, and then don't forget your plus c at the very end. So we just used, where did it go? Right at the top of this, oh, it's the one that we circled actually, where we have to divide by that k value. All right, so we divided by the 4, and now we can simplify this statement and write it as 2e to the 4y plus c. Don't forget, I'll probably remind you of this more often than you want me to. You can check this answer by taking the derivative of it. Let's take the derivative. I've got 2e to the 4y, so that if we take the derivative with respect to y, and we factor the 2 out, and then we multiply it back in, so you've got 2e to the 4y, and then don't forget you have to use the chain rule and multiply by the derivative of the exponent. What's the derivative of 4y? It's 4. And what's 2 times 4? Well, that's 8. So you'd have 8e to the 4y. You sure would. Sure would. So just a quick example that you can indeed take the derivative of your answer to an integration problem, and you should get the original integrand again. What else? What else do I have for you? Another couple of pages worth of goodies. Here we're taking the integral of x to the negative first power with respect to x. In other words, the integral of 1 over x. And you might remember that the derivative of the natural log was equal to 1 over the variable. So that was the derivative of the natural log of x equaled 1 over x. So here we're integrating, so we take the 1 over x, it turns back into the natural log of x. Don't forget the plus c at the end of the integral. And here, our variable, the x in this case, is being written inside of absolute value bars. Those are important because you can't take the natural log of anything other than a positive number. You can't take any kind of a log of anything other than a positive number. So if your x value turns out to be a 0, then you're still in trouble on this one because you can't take the natural log of 0. It has to be positive. But those absolute value bars will help you out in the majority of cases. Let's utilize that in finding a solution here in example number 3. Let's distribute this integration process to our two terms. So we have the integral of 7x minus 4 with respect to x minus the integral of 8x to the negative 1 with respect to x. That is a bad integral symbol. Let me fix that. There we go. And now we could use that constant multiple rule, so we could factor the 7 out of the integration process. 7 times the integral of x to the negative 4 with respect to x minus 8 times the integral x to the negative 1 with respect to x equals, now we're going to keep the 7 times, I'm going to keep my variable, I'm going to increase the exponent by 1, negative 4 plus 1 equals negative 3. Don't make that mistake, don't put it as a negative 5. And then we have to divide by the new exponent, negative 3. Great, minus 8 times the derivative of x to the negative first power is the natural log of the absolute value of x. And then don't forget your plus c. We'll clean this up just the tiniest bit and we'll have ourselves a final answer. X equals negative 7/3. You could write this as x to the negative third power. You could write it as negative 7 over 3x to the third. And don't forget that plus c. You'll make your teacher or instructor or professor extremely happy if you never forget a plus c. In fact, if you do remember the plus c consistently, that'll keep them off your back. How about that? It's like an apple a day keeps the doctor away. A plus c at the end of every indefinite integral will keep your professor off your back. They'll love that. You'll love that. Don't forget plus c. Yeah, I don't know. This is not exciting. Let me just rip through this one real quick. I'm going to factor out the 1/6, and there's the integral of the x with respect to x, plus factor out the 6 times the integral of 1 over x with respect to x equals 1 over 6 times x, increase the power by 1, divide by the new exponent, plus 6 times the natural log of the absolute value of x, plus c, simplify. Let's write this one as x squared over 12 plus 6 natural log absolute value of x plus c. There's another solution for you in case you want to attempt that one on your own. And then finally, an applied problem. When I teach this course, if you're one of my students, you know that you're in an elementary calculus course, which is sort of casually referred to as a business calc course. And we like to see applied problems, especially that pertain to business. So you're not going to be surprised. My students aren't going to be surprised to see the phrase marginal cost written here. And we've talked this semester already about the fact that marginal cost is the derivative of the cost function. Except now we're doing it in reverse. We're being given the marginal cost function, and we have to find the cost function. Let's try it. Normally, if I told you to find the marginal cost function, you would take the derivative. Now I'm giving you the marginal cost function and asking you to find the cost function, which means you have to take the antiderivative, or the integral. So the integral of the marginal cost function, integrating with respect to x, means I'm integrating 10x minus 5 with respect to x. And you could see that entire expression in parentheses. And what we want to do now is integrate. Let's distribute our integration symbol. It's the integral of 10x minus the integral of 5. And I should have, sorry, put a little dx in there. Here a dx. There a dx. Very good. Okay. And then now I could factor the 10 out of that integration process. And we said that when you take the integral of the variable, we need to increase the power by 1, so that becomes x squared, divide by the new exponent, good, minus, and this is what I meant to say, that we said that if you're integrating a constant, the solution there is going to be the constant times whatever you're integrating with respect to. So in this case, you'll get a 5x. Certainly the derivative of 5x is equal to 5. That's easy to check our work, and include the plus c. Let's clean this up a little bit, and since we can reduce right here, let's write this as 5x squared minus 5x plus c. Now, this is a variable, and since what we've just designed is a cost function, c of x, the fact that this is a variable right here tells me that that's a variable cost. There's a variable here, so this must be a variable cost. This thing, however, oh boy, what am I trying to do here? Put that back. Yep, I just wanted to get rid of this. There we go. Which means, since this is not a variable, it's a constant. Constant's the opposite of variable. Constant, fixed cost. This constant variable represents our fixed cost. An example of a fixed cost might be the cost of electricity. Even that can vary a little bit. How about the cost of rent? At least from year to year, the cost of renting whatever brick and mortar you're working out of, that should remain fixed. So it's not impacted by the variable, and this problem tells us that our fixed cost is $2. So I'm going to take that $2, I'm going to make myself smaller first, sorry about that, and that fixed cost is going to become 2. So we can write our final cost function as 5x squared minus 5x plus 2. So the cost of producing 0 units would be $2. What is this, a lemonade stand with numbers that small? Come on now, fixed cost of $2. Maybe this whole thing is in terms of millions. I like the sound of that better. All right, so that is our one and only applied example for this section. I do believe that puts us at the end of these notes. It does indeed. And I got to tell you, it's been a pleasure to introduce the antiderivative process to you. Stay relaxed, stay loose, come back to this as many times as you have to. Remember that this is, for the most part, just the reverse of something that you've already been doing. It's going to take a little bit of practice, but my recommendation to you on this one is repetition. Go and practice a bunch of these problems. If you have to take some short breaks, take short breaks, but don't take a lot of breaks. Keep coming back. Keep increasing the exponent by 1 and dividing by the new exponent. Increase the exponent by 1, divide by the new exponent. Go and find some problems where you have to integrate some exponential functions where you've got e to the power of whatever. Okay? Make yourself some flashcards. Start yourself some kind of a review packet on this topic right away. Go back through these notes, pull out the bulleted things, the things that were highlighted, the things that were in those tan colored boxes. Start building that sort of formula sheet right away. Include an example problem that goes along with each one of those generalizations in those sand colored boxes, because you want to be able to go back and look at that information and have it all in one place instead of having to flip through pages and pages of notes to try to find them, okay? You want all that information to exist in one place in your brain, so start out by putting it all in one place on paper. All right, no more preaching from me. Nice to see you again. See you later.